Hi, my name is Greg Mead. I'm a faculty member at Santa Fe College in Gainesville, Florida. This is the third, I believe, of several videos that I'm making on geologic time and how we actually use the various techniques in geologic time to figure out how old things are in geology. I'm not sure if I've explained this yet, so let me tell you how you get to the web page that I'm about to show you. You probably cannot read that link, but I will include it in the material underneath this video. Once you get to this point, the easiest thing to do is to click on either GLY 2010, which is geology, or onto ESC 1000, which is Earth and Space Science. Once you click on that, scroll down and click on the class lecture schedule. Once you've clicked on that, scroll down until you see geologic time, and you'll reach the geologic time webpage. Feel free to explore around this. In the other videos, I have extensive referrals back to this. It should be kind of fun. In this particular case, we're going to start talking about radiometric dating. And so what we'll need to do is to scroll all the way down to this point, past radioactive decay, to this point. And you could, if you want, do a search for hourglass decay and you would get it. Okay, so what happens when materials decay in radioactivity? Well, the simplest thing to do is to start by a somewhat different process, and that process is what happens when sand trickles out of an hourglass. Sand trickles out of an hourglass at a constant rate, and if you measure the amount of sand in an hourglass, it will decrease in a linear fashion. And if you know how long it takes for it to all go out, all you have to do is measure the proportion that you have to know how much time has passed. The problem is, as it says here, radioactive decay is different. And what happens with radioactive decay is that we have a material which decays at a specific rate dependent on two things. Dependent on which isotope we're dealing with, and that's not something you can really control. That's something that has to be checked empirically. And then we can also look at how much of the material we have. Let's suppose that we have 1 kilogram of a radioactive isotope. If we measure how fast that material is decaying, we might find, for instance, that it's decaying at 1,000 decays per minute. There are ways of actually measuring that. One well-known device that does this is called a Geiger counter. Well, the decays occur randomly. There's no way to tell which atom within this radioactive material is going to decay, so it is a statistical process. The odds are that sooner or later every atom will decay, but we don't know which one. And that means that if we look at this 1,000 decays per minute, those 1,000 decays per minute will be distributed throughout this material. Now, there are two things we can do. One thing we can do is we can cut this in half. And if we cut it in half, we have 1/2 kilogram. But because the decays are random, that means that if we now have half as much material as we started with, we will also have half as many decays because the other decays would be occurring somewhere else. And so 1/2 kilogram of material would be decaying only at 500 decays per minute. Additionally, if instead of cutting this in half physically, let's just wait until half of the radioactive isotope has decayed away. If instead of cutting it in half physically, we just wait until eventually half of the material is left, then that will also result in a decay rate of 500 decays per minute. Now that we have 500 decays per minute and a half kilogram, if again we physically cut this in half so that we have a quarter kilogram, we're removing this, and that means that 250 decays per minute are elsewhere, and we're only going to have 250 decays per minute in this quarter kilogram. By the same token, just as we did before, if instead of physically cutting this in half, if we just wait until half of the isotope has decayed away, and we now have a quarter of a kilogram instead of the half kilogram that we had, this also means that the rate of decay will decrease. And the overall result of this kind of process is something that in mathematics says that the decay rate is dependent on the amount of isotope. The more atoms you have, the faster overall it's going to be decaying. As the number of atoms decreases, the rate of decay will decrease proportional to the amount that you have. And that means, and I'm just going to turn this off for a moment. Okay, I've turned this off. That means that if, for instance, we make a graph, and let me make sure that all this is visible in the camera, and it is, okay. If we start with a certain amount of material, it's going to be decaying at a certain rate. It's going to be decreasing. If we wait until half of it decays, and that's going to take a certain amount of time, by the time we get to half of the material that we started with, it's only going to be decaying half as fast as it was initially. And so the slope of this line will be less. Because it's decaying more slowly, it will again lose half of what we had to begin with in the same amount of time. And so it's going to go down to 1/2 of what we started with in the same amount of time. Now that we're down to, this is all of it, 100% we could say, this is a half of it, this is a quarter of it. Now that we're down to a quarter of it, it's only going to be decaying a quarter as fast as it was to begin with. And that means that it will again take this same amount of time to lose half of what we had. And the net result is that over time, it will decay more and more and more slowly. But it will always take the same amount of time, no matter where we start, it'll take the same amount of time to lose half of what it had when we began that. And so this amount of time, the amount of time it takes to lose half of what you started with, is known by a name you've probably heard. This is the half-life. Oops, yes, the half-life. And this is a characteristic of radioactive materials. All different radioactive isotopes have different half-lives depending on the physics of what's going on in the nucleus of those atoms. Some atoms take a long time to decay. Uranium-238, for instance, takes, I believe it's 4.5 billion years to go through one half-life. There are half-lives that are even longer. There are half-lives that are much shorter. Certain artificial isotopes take fractions of a second to decay by one half-life. A well-known isotope you probably heard of, carbon-14, which is responsible for what's known as carbon dating, has a half-life of 5,000, I believe it's 5,730 years. So this is what happens. And so let me go back and restart our projector, and we can take another closer look with somewhat better drawn images than what I just showed you. Okay, so what this means is that as a radioactive isotope decays, as you go through 1, 2, 3, 4 half-lives and so on, the amount of isotope you have left from when you started goes to a half, then a quarter, to an eighth, to a 16th, to a 32nd. So what are we doing mathematically? What are we doing to the amount after 1 or 2 or 3 or 4 half-lives? How do you get from a half to, or from 1 to a half? You divide by 2. How do you get from a half to 1/4? Guess what? You divide by 2. How do you get from 1/4 to 1/8, or 1/8 to 1/16, or 1/16 to 1/32, and so on? What are you doing each time? Okay. And that is what happens during the time period when half-lives elapse. When will you reach 0? Well, how many times do you have to divide something by 2 to reach 0? The answer is actually an infinite number of times. And so, in theory, we never reach 0. In reality, eventually you're going to have 4 atoms, then you're going to have 2 atoms, then you're going to have 1 atom. You cannot go down to a half an atom. And so eventually you would. But in any reasonable size sample, if you have a couple of grams of a radioactive isotope, you will have many, many, many trillions of atoms. And so you don't need to worry about reaching 1 atom and then a half atom. So don't worry about that. Now, what happens to the isotope? As we saw when we looked at radioactive decay, the isotope doesn't just vanish. It doesn't go from 1 to a half to a quarter to an eighth, and there's nothing else. Instead, it turns into another isotope. It always turns into another isotope. The isotope that radioactive decay produces is called the daughter isotope. And for every atom of a radioactive isotope that undergoes alpha decay or beta decay or electron capture, for every atom that undergoes those decays, it produces a daughter isotope. And so the daughter isotope increases as the parent isotope, the radioactive isotope, decreases. So as the radioactive isotope decreases, the daughter isotope increases on a 1-to-1 ratio. So if you have a half of what you started with, you start with 100% of something, and you now have 50% of what you started. How much is turned into the daughter isotope? Very simple arithmetic. Now, in our calculations today, we are largely going to assume you have exact half-lives elapsing. The mathematics becomes much more complex, and you need calculus if you are going to figure out what happens after 1/3 of a half-life, or 2/3 of a half-life, or 0.5796 of a half-life. But we're going to assume whole half-lives have elapsed in making our calculations. But I do want to show you, suppose that you start with a particular amount of an isotope and you wait, it doesn't have to be until you have a half or a quarter or an eighth. Suppose you wait until you have 32.84% of what you started with. How much has been turned into the daughter isotope? Well, it's going to be 100 minus 32.84, which is going to be 67.16% if I've done the math in my head right. But you see the idea. This is how you calculate the amount of daughter isotope that you have left over. Okay, so how can we use this? Well, the way that we're going to use this is we are going to look at the fraction that we have left over after a certain number of half-lives. And suppose that we have, let's suppose that we have 1/64th. And I chose that number on purpose. Suppose we have 1/64th of what we started with. How much would be left over? How much would there have been one less half-life than that? Well, we would double that, and we would have had 1/32. How much would we have had if we had one less half-life than that? We'd have 1/16. What am I doing each time? I'm multiplying that by 2, that fraction by 2, which gives us 2/64ths, which would be 1/32. This would be multiplied by 2, 4/64ths, which is 1/16. And again, we would see that as we go back in time, we have more and more and more of the original isotope. And how many half-lives have we now had elapse? Well, that would be one half-life. That would be a second, a third, a fourth, and a fifth. 1, 2, 3, 4, and 5 half-lives. So simply by going through the splitting in two of the amount that we had to begin with, or by back calculating, multiplying till we reach the amount that we started with, we can then calculate how many half-lives have gone by. If, say, 5 half-lives, or say 5 half-lives in this case, if 5 half-lives have gone by and each half-life is 3 million years, how much time has elapsed? Each half-life is the same amount of time. So we have gone through 3 million years, another 3 million years, another 3 million years, another 3 million years, and another 3 million years. How do we figure that out? Besides saying 3 million plus 3 million plus 3 million plus 3 million plus 3 million? 3 times 5. I think you guys can all figure that out. So that's how we calculate how long it has been once we've gotten the number of half-lives. Now, one problem with this is that when we look for the amount of isotope that we began with, it's not always easy to figure that out, because when we analyze a sample, let's say we get a sample of obsidian, and we measure the amount of uranium, or we measure the amount of radioactive potassium, or any of a variety of different radioactive isotopes, it's hard to know how much was present at the beginning. There are ways of doing that, but it's often hard to figure that out. So how would we go about getting the original amount of isotope? There is another thing that we can do. Remember that when we looked at this, we discovered that as the amount of parent isotope goes down, the amount of daughter isotope goes up. If that's the case, then if we can measure the amount of parent isotope and the amount of daughter isotope. If we started with 0 daughter and it was all parent, then measuring the ratio between the two will give us an idea of how many half-lives have gone by. Let's take a look and see how we would do that. Suppose that at the beginning, we look at the amount of daughter and the amount of parent. If this is a brand new sample, then the amount of parent is going to be 1 or 100%. The amount of daughter would be 0, assuming there's none to begin with. After 1 half-life, the parent has decreased to 1/2. And we saw earlier that 1 minus 1/2, we actually had 100% minus 50%. 1 minus 1/2 is equal to, of course, 1/2. And so the daughter has increased from 0 up to 1/2. And what's known as the daughter to parent ratio, which is what's usually measured, here would have been 0 to 1. Here would have been 1/2 to 1/2, which is the same as 1 to 1. After 2 half-lives, our parent has decreased down to 1/4. So how much has turned into the daughter isotope? Well, all the rest is now the daughter isotope. And that means 3/4 of the isotope is now the daughter isotope. And so we now have 3/4 daughter isotope, 1/4 parent isotope, and the ratio of daughter to parent is now 3/4 to 1/4, or 3 to 1. Now, when you do this in a homework assignment or an exam question, it's really important to show that you know every single step. And so you need to actually do that visibly so that your instructor, in this case me, understands what you did. For instance, where did that 1/4 come from? And after 2 half-lives. And it came from the fact that after every half-life, the amount that we have is divided by 2. And so if we start with 100% or 1 all of something, after 1 half-life, we've divided by 2, and that gives us 1/2, which is how much we have after 1 half-life. After a second half-life, we again divide it by 2, and that gives us 1/4. And by doing this, you'll show to yourself where the numbers come from. You're less likely to make a mistake, and you're also demonstrating to your instructor, in this case, if you're in my class, me, that you know what you're talking about. Okay? So how do we use this information, and specifically, how do we use the daughter to parent ratio to tell how old a sample is? And we can use, as an example, a daughter to parent ratio of 15 to 1. So suppose that we've analyzed our sample and we have a daughter to parent ratio of 15 to 1. Where does that come from? And how do we use that to get the number of half-lives? Well, we can make a table or a chart where we start with the amount of parent, the amount of daughter that we get from that, and then the daughter to parent ratio. And at the beginning, it's all parent. We have no daughter, so our daughter to parent ratio is 0 to 1. After 1 half-life, we've divided our parent by 2, so we now have half of what we started with. and by subtracting that from the amount that we started with, we get the daughter, and so we know we have 1/2 daughter, and 1/2 to 1/2 is the same as 1 to 1, which we showed a few minutes ago over on the right-hand side. After 2 half-lives, we divide this by 2, and we get 1/4, and all the rest has turned into the daughter. And so 3/4 is now the daughter, and so a ratio of 3/4 to 1/4 is 3 to 1. After 3 half-lives, we again divide that by 2, and we now have 1/8 as much parent as we started with, and all the rest, again, has turned into the daughter. And so the daughter can be calculated by 1 minus 1/8, which is, of course, 7/8. So our daughter to parent ratio is 7/8 to 1/8, which is 7 to 1. After 4 half-lives, we again divide that by 2, we get 1/16. All the rest is turned into the daughter, and so 15/16 of our original parent has now turned into the daughter through radioactive decay. And so our ratio of daughter to parent is 15/16 to 1/16, which is the same as 15 to 1. And this tells us, because that's what we've measured, that we've had 4 half-lives elapse since the beginning of our time period. If the half-life was of this particular isotope was, just for the sake of argument, 10 million years, how old is this sample? Well, it's gone through 4 half-lives. Each half-life is 10 million years, so 4 times 10, obviously 40 million years old. And if you have a daughter to parent ratio of 15 to 1, and, excuse me, and a half-life of 10 million years, then you have a 40 million year old sample. Okay, so this is how you're going to do these problems in general. You won't get 13 to 1 or 14 to 1 unless you're doing this with calculus. You'll always have a ratio which will give you an even number, at least in my problems, will give you an even number of half-lives. But then the question becomes, suppose it's not easy to measure the amount of parent. Well, what can you do? And this is, for instance, a problem with carbon-14. The amount of carbon-14 in any given sample is very, very small. So what can we do in a case like that? Well, it turns out that even though it can be very difficult to measure the amount of a radioactive isotope, sometimes it's very easy to measure how fast that isotope is decaying. And if you recall, when we were talking about this, it turns out that the rate of decay is always proportional to how much you have. So if you start with a decay, an amount of 1 kilogram, and for this particular isotope, it happens to be decaying at 1,000 decays per minute, eventually, after 1 half-life has gone by, you're going to have half as much as you started with. You're also going to be decaying half as fast. After 2 half-lives, you're going to be down to 1/4 as much as you started with, but your rate of decay will also be 1/4 of what you started with. And because of this, we don't have to have the amount of radioactive isotope. Instead, we can use the amount or the rate of decay. If we know how fast it was decaying at the beginning, and we can tell how fast it's decaying now, if it's decaying 1/4 as fast as it started out, that means 2 half-lives have elapsed. If it's decaying 1/8 as fast as it started, that means 3 half-lives have elapsed. And so we can use the rate of decay as a proxy, as a replacement for the actual amount. And many times, that's going to be easier to measure, physically measure, than the actual amount of radioactive isotope that we have present. So under certain circumstances, and again, especially with carbon-14, we generally use the rate of decay instead of the amount of isotope that we actually have as a proxy for the amount of isotope that we have. And from that, we can get the number of half-lives. Okay. So these are the various techniques that we use in a very simplified manner to getting radiometric dates. The question then becomes, can we always get a radiometric date on any sample? And the answer to that is no. We need certain circumstances, certain conditions to be present in order to do that. And if you scroll down to the bottom of this webpage, you're very close to the bottom, you will see what I call caveats or warnings that show the principles, or rather show the conditions that have to be present in order to successfully do radiometric dating. And so these are the principles. Let's go over these. The first is you have to have a closed system. What does a closed system mean? Well, suppose you have a rock here, and this rock allows atoms of your parent or your daughter isotope to migrate in or migrate out. If that's the case, then you don't have an accurate idea of how many half-lives have elapsed, because you can't accurately tell how much of the parent isotope you started with versus how much you have now, and the daughter isotope is often helpful for that. So how do you make sure that you get a closed system? Well, imagine that we have a rock like this. This is a nice example of a basalt, which is an igneous rock, but this rock is quite gray in color. This has been weathered, and the weathering process is one of the things that tends to result in ions being and atoms being mobilized so that they can either leave or come into a rock. So weathering is not something that you want to have in the sample that you're testing the age of. Well, remember that sedimentary rocks are the result of weathering. And because of that, sedimentary rocks are usually a very poor choice in figuring out radiometric dating. You want to avoid you want to avoid sedimentary rocks. Metamorphic rocks, remember, are the result of heat and pressure and crystallization that results from that. And if you heat up a rock and if you place it under a lot of pressure and begin to crystallize or recrystallize it, then again, atoms and ions can migrate either into or out of an already existing rock, and the net result is it won't be a closed system. So the best thing to use for radiometric dating is typically an unweathered piece of igneous rock. And by unweathered, that means either a nice fresh piece like this, or one where you find a large igneous rock and cut it out until you can take a piece of rock out of the center that has not been weathered. So that's, generally speaking, what you want to do to make sure that you have a closed system. The second thing that you have to be concerned about is the number of half-lives that have gone by. Because remember that as more and more and more half-lives go by, you have less and less of the original parent isotope. And I'm going to just very quickly turn this over here, and I'm going to write out how much you have after more and more half-lives. After no half-lives, you have the full amount. Then you have half, then a quarter, then an eighth, then a 16th, then a 32nd, then a 64th, then 1/128th, then 1/256th, then 1/512th, then 1/1024th, and this is after 1 half-life, 2 half-lives, 3 half-lives, 4, 5, 6, 7, 8, 9. After 10 half-lives, you've got less than 1/1000th of what you started with. And because you have less than 1/1000th, it's very difficult to measure. And as a result, generally speaking, after 10 half-lives, you cannot accurately measure the amount of parent isotope. So this is a limit. Certainly after 20 half-lives, less than 1/1,000,000th of the original parent half-life is left. And the net result is it's almost impossible. Under rare conditions, you can measure up to 10 half-lives. But after 20 half-lives, you really can't measure the amount of parent isotope accurately. Any measurements that you get will be the result of contamination or of inaccuracies in your measurements. And so they're not valid measurements. And the net result is that generally we say that after 10 half-lives, you cannot measure the amount of parent isotope accurately, and that's a limit to how far back in time you can go. Now, many isotopes have very long half-lives. The half-life of uranium-238 is the age of the Earth, and so that's not a problem. But there are some half-lives, for instance, carbon-14 has a very short half-life, less than 6,000 years, and as a result, we can only go back maybe 60,000 years with carbon-14. And anything that's older than that, for instance, dinosaurs, we can't measure because there's simply not enough of the parent isotope left to accurately get an idea. Okay, number 3 in our caveats. Number 3 is you must be dating the correct event. What does that mean? Well, let me show you an example of a rock that we have here. Here's a nice example, and I'll try to bring it close so you can see it. Hopefully that's a nice example. This is a conglomerate. It's composed of pebbles. Suppose that we take one of these pebbles, and suppose that that pebble is a nice piece of an igneous rock, and you can get a good radiometric date on it. What does that tell us? Does that tell us how long ago that pebble wound up in this conglomerate? No. It tells us when that pebble, the granite that pebble, or the igneous rock that pebble came from, crystallized from magma and got sealed off. It doesn't tell us when it broke off, when it rolled into a river, when it was transported down a river and was rounded off to make these nice rounded pebbles, and then wound up in this conglomerate and got solidified or lithified into this sedimentary rock. So the event that you're measuring, if you measure how old that pebble is not when did it turn into a pebble, it's when did it crystallize from magma, okay? You have to be careful about that. If we find, for instance, an arrowhead, I don't have any arrowheads lying around. If we find an arrowhead made out of obsidian, and this is obsidian. Obsidian is a great material to measure radiometrically because when it's hot and still magma, liquid, any argon can escape. Argon potassium measurements can give us a very good idea of the age of this. If you find an obsidian arrowhead and measure the argon potassium age, you're not giving the age of the arrowhead, you're given when it came up out of the ground and solidified into obsidian. Okay? So those are the key points to think about when you are doing radiometric dating. Make sure that you have a sealed system, and that usually means an igneous rock. Make sure that you have usually less 10 or less half-lives, unless you're using very specialized techniques, and make sure that you're dating the correct event. If all of those things are correct, then you have a good chance of getting a good date for using radioactive decay. If you don't have all of those, then you're running the risk of having an invalid date. Okay, I hope these videos are helpful. If you have any questions, then put them down in the comment section, and I will do my best to answer them.